Okay, it's time to get started. So, any question from this time? Yeah, this time we finish this QM1. We talk about all the measurement and okay. So we have something extra. So we also talk about this block sphere interpretation of 1 qubit. And it's a nice way to see the more structure about the polys. So we think about polys, the poly xyz kind of correspond to the block sphere xyz. So there is sigma x on x-axis, sigma y on y-axis, and sigma z on z-axis. So those three sigma kind of measure the spin in those three directions. And then you have the corresponding eigenvalues that we think as a point on the sphere. And those are in homework, so you probably have a good practice now. And just besides just those three axes, then we can think about measurement and the state in random in arbitrary direction on this surface. And so a poly operator, so the measurement corresponding to a direction, say n x n y n z, is actually is n hat sigma, and and the corresponding eigenvectors we're writing in a funnier way. So it's cosine theta over 2, 0 plus sine theta over 2 ei phi 1. So it's a little different. So the polys we are returning this Cartesian coordinate x, y, z, and the state is in sigma phi. It just happen to be easier to write this way. But you can check this sigma phi notation. It is consistent of the x, y, z we think about. So you put the corresponding sigma and phi for this x-axis point and the y-axis point and this z-axis point, and you should see there should be the eigenvectors of sigma x, sigma y, sigma z. And in the homework, you should check that this general form is the eigenvector of this general form. Okay. And okay, so that's the block sphere, and then we go to P of n. Oh, yeah, and I should have already uploaded this, so that's fine. And later there will be a little more about the block sphere we will talk about when we talk about density matrices. But for now, we back to measurement, and we talk about this P of n measurement, basically just generalized measurement, but we lose a little bit information. So instead of saying or describing the measurement with all those mi, we just describe with ei, which is basically the square of mi. Okay. And we lose some information because when squaring, for example, we will lose the minus sign, etc. And it's matrices, so we will lose a little more. But okay, so you get this ei, then you can still calculate the measurement probability, but then you don't know the post-measurement state. Okay. But sometimes if you just want to know the measurement probability, then those ei are easier to use. And then here we give a little example of how to use ei to describe something. So we have like this imperfect distinguishment between one state and zero state and plus state. And so we have E1, E2. E1 is a projected onto 1, scale to something, and E2 is projected onto 0, scale to something, and E3 is identity minus those two. So you can see that it's easier to construct the P of n because they're a little easier than constructing a measurement instead of mi because they sum to identity. So they have this sum to identity. Their normalization is sum to identity. So for whatever remaining, you just need to have identity minus. So you have some P of n, then you want to complete, you just have another P of n that's the identity subtract or everything you already have. Okay? Then it should be complete. But you need to check that E3 is positive. Okay. Okay. And this is this, and we have non-cloning theorem. Okay. And okay, so here, well, the ordering is a little funny, but so we talk about all this information theory, then And then we'll go to this measurement theorem about measurement, and we'll go back to more information theory. Okay, so I should probably put this in front. But anyway, okay, and we go over this a little bit last time. But here, now let's go over this again a little more carefully. So we want to prove this theorem about generalized measurement. That says that you can always get a generalized measurement by doing a projective measurement on a larger space. And so a larger space means like this. So you have a system, your Hilbert space Q that you want to do your generalized measurement on. And then we have this ancilla system. So it's a big enough quantum system. So we just put it here and we'll initialize it into some standard state. So let's say that's 0. And it's big enough so that it has a base, also known basis m, where this m corresponds to your measurement indices m. So whatever number of measurement operator you have here, the dimension should be at least that big on your ancilla system. Yeah. So I think your system is initialized in some psi that's to be measured. So this psi is whatever state, and your ancilla system is in some standard thing 0. This is a system you prepare to help you do this measurement. And we want to say we just use projective measurement on those two systems together, and should give you the generalized measurement on Q. And how we do this is okay. And how we do this is so the generalized measurement, once again, we think about those psi should, after a measurement, should become m sub n psi with some probability, with the probability being this thing, the norm of this thing. Okay. So there are m different outcomes, and when you give this small m outcome, your state should become this big N sub n psi. Okay. Where we use this notation to describe two things. Means that the probability of getting this is non-square, and the state is this thing renormalized. Okay. And anyway, so we want to do this, but those mm are not projective. So what we do is we do a really weird unitary. This is big U. The big U is a function of this set of measurements. Sorry, not set of this measurement, which is set of measurement operator. So this U acts both on your Q system and M system, and we have a partial definition here. So this is star. So Q must satisfy this relationship, and it says that U act on the initial state, so your psi and 0. I want to turn it into summation m, and on the Q system, I want it to become this state, and for every different m, I want to have the n and the ancilla system go into this orthonormal basis state m. Small m. Yeah. So each one of those are kind of orthogonal because you get different m here. Yeah. And later we'll measure this register and say that basically that will force the Q part into this state, and you get your generalized measurement. Okay. And so first we need to check that this U is this U actually exists. So, and the first thing we check is that under this condition itself is consistent. So if you put different psi, so we want to check if you put different psi here, maybe use a different color. Use this. So want to see that if you put different psi here, then you will get this U is unitary, so you will preserve inner product. And we do that, so you can do the inner product on the left hand side and the right hand side and see they are the same. Okay. And because the unitary should do this. Okay. And so yeah, on the left hand side. So if U is actually a unitary, then it should be this inner product of psi 0 and phi 0. Okay, and yeah. Yeah, so on the left hand side, if U is actually a unitary, this should be this psi 0 inner product with phi 0, and this should be equal to this inner product between psi and phi. And on the right hand side, then we do this little ugly calculation. So we want the inner product of this and the inner product of this, and there are a lot of indices, so you are summing over m and m prime. So there is a summation m from this psi and psi summation, and there's summation m prime from this phi equation. And yeah, so we put phi in front here and the psi here, so there's a m prime dagger and m prime. And now we use the orthonormalness, so we use those m are actually orthonormal vectors. So this inner product between m prime and m is delta m prime, or in other way, is 1 is non-zero only if m prime equal to m. So we are actually just summing over m. Okay. Yeah. And and yeah, so we are just summing over m, and you have phi and psi, and is some and dagger and in the middle. Then we use the completeness of the measurement m. So this is just that, and you can you put all the let me change the color. So you pull the summation inside, because those two things are the only thing that depend on. Okay, maybe let's use it. So those things are the only thing that depend on your indices m. So you can pull the summation inside and do the summation and see their identity. So this is just inner product of phi and psi, and so that's what we expect. Okay. So we know that at least when we restrict the second register to sorry, I got confused between when we restrict the second register to being 0, then this U is preserving inner product, so that's nice. And then we can but you can do so the thing is, you can do whatever when the second register is not 0. So if this is 1 to n, then we don't really care what you do here. And because we have a lot of freedom, so we can complete U. We can always complete U to a unitary. Yeah. And so the mental picture is kind of this. So U is acting on this really large space. So you have multiple columns, right? And so U is acting on this space Q times M. This is a really large space, and we are saying so when U acts on whatever, so psi tends to 0 space, so psi tends to 0, this is so so we can kind of cut U into blocks, right? Like cut blocks depend on what the second register is. So you have something tends to 0, something tends to 1, to something tends to m, like this. And now we have checked the something tends to 0 part, preserve the inner product. That means all those columns are also normal to each other. And we are saying the other columns are kind of whatever. So you can always complete U to a unitary. And this used to be a homework, but I think this problem is a little boring. So maybe we'll get rid of this this week. About homework. Anyway, let's finish this proof. So I claim that U can always be extended into a full unitary, because you can just fill in whatever. Okay. and this is a basic linear algebra that you have some set of linear independent things, then you can always extend it into 4 bases that span your whole space. Okay, so and we know that if every columns, okay, I guess we didn't really say, but you can check it really easy that if every column is also normal to each other, then U is a unitary matrix. Okay, and okay, so that's a proof. And okay, so we claim that this U exists. And finally, now back to doing our measurement. So our U will do this thing. And let's see what happens when we measure the second register on a projective measurement. And so on a second register, you do a projective measurement that corresponding to measurement operator being this M tensor M. And you really do nothing on the first register. So the measurement operator on the whole space should be identity on Q tensor this projector on M. Okay. And so the probability of outcome M. So yeah, so now we check everything. So we need to want to check the probability is like the yeah. So want to check the probability distribution is what we will predict from the generalized measurement, and we want to check the post-measurement state is the same as what we expect. Okay, so let's check the probability. Do we check this this time? But anyway, yeah. Yeah, so our state, once again, so maybe, let's write this down here again. So, as a reminder. So, U psi 0 equal to some M. Big N, small m, psi tensor M. Okay, and yeah, so so we want to calculate the post-measurement probability, and this is projective. So the probability is a little easier. So in the middle part, we just have the projector here, and want to sandwich it with our post-measurement state. So this U psi 0 and U psi 0 dagger actually equals psi 0 U dagger. And as we say, this U psi 0 is this whole thing. And so we are writing down everything. So our PM here become the middle part. So maybe let's use a color. So this PM. This PM become this thing we are just writing it out, and so we already have M here, and so M corresponds to the M's outcome, and so we want to change our name of non-variable. So we have M prime and M double prime, and for the later part we call it M double prime. So just this thing, but every M has double prime, and the previous part we also have double prime. So that's the psi M double. M prime dagger tensor M prime. Okay. And now we see basically everything is tensor, so we just do this inner product slot by slot. So first slot should be this psi M prime dagger IQ and double prime and psi. But the second register we have M prime and M double prime. And that's two delta function here. So delta function on M and M prime, and delta function of M and M double prime. And anyway, and then when you sum over M prime and double prime, and you see that from the also normalness of these bases, that just means this M double prime should be equal to M, and this M prime should be equal to M. And yeah, so every N should just be M. And so you have psi M sub M dagger and big N sub small n psi here. And yeah, and second register you get 1. This is a number, so you don't care. Okay, and yeah, and finally you see that this is what you expect on your generalized measurement, right? So you can check the previous chapter or you just see that this is, so you check it out. This part is the subnormal matrix, and this is its non-square. So this is the probability of generalized measurement you expected. And what about the post-measurement state? And the post-measurement state is, okay, so your operator on your state. Okay. And so you put this thing on this thing, and once again you have the, yeah, sorry. Okay, yeah, I guess we are skipping steps. But anyway, you put this thing on this thing, then you see there is inner product of m and some m prime here. Then you see that you get this thing. Yeah, so the first register, because you add identity on this n sub m, so n sub m side, and that's just n sub n side. And the second register would be projected into m, right? Because you're projected on m, so it must be m here. Okay. So the q part is this thing, and the m part is the state m, saying that the outcome is this small m. And the normalization is the square root of this probability. Okay. And then we see that those two parts are just tensoring each other, and we can, so they are not really doing anything to each other, so we can just, if you throw out the m part, then we see the q part is just the state that you expected. Yeah. So yeah. So the m part is just on classical state, computational basis state, so you can throw out. And on the q part, then you just get this post-measurement state that you expected from your generalized measurement. Okay. Yeah. And so that's it. Once again, as a summary, to do the generalized measurement, you first introduce this and see that recorded register. Then you apply the unitary on the drawing system, this Q tensor M. And this is, you will basically do the measurement. It has the info about the measurement you want to do. And then you measure the record register in computational basis. And you either ignore or throw out the record register, and you will see that on your original register, you have done your generalized measurement. Okay. So any question about this theorem? If not, we will go back to more information theory. But okay, before information theory, I have some organization thing to say. So okay, let's see. I think this Thursday is actually a holiday, right? It's Teachers' Day, so we'll have no class, and okay, that's good. But then our homework, let's see. I think we will probably. I think we can have you can probably all turn in your homework online, so that's fine. But the homework out, I think we can have a really short homework out. So yeah, so next week is okay. Yeah, I will ask the TA to have a really short homework out, and yeah. So I think you can probably turn in the homework either online or earlier to the physical box before you go on holiday, and yeah, and we'll have short homework. Let me see, or little. So I have homework out, and yeah, that should be fine. Yeah, let's have a short homework out this week, and you will post sometime Thursday. Okay, that's okay for everyone. So holiday, but let's keep the homework going. I think that's easier. Okay, and so that's that. And okay, let's go back to information theory. information theory. So we have information theory that's well, I guess it's not quite information theory, but now we want to talk about some application of entanglement. Okay, and entanglement, we are going to see that they have those properties. So it's some kind of a long-range correlation between two systems. So it's kind of like classical chain randomness, if you know what it is. But it's more powerful than chain randomness, but we will not be able to show that today. But there is some example in the textbook, also in chapter 2. And but just like chain randomness, it contains no information. And yeah, we are going to see what this means later. Okay. So we have applications of entanglement, and first is super dense coding. Okay. So this is something you cannot do with. I guess this is already something you cannot do with chain randomness. Sorry. Yeah. Yeah. So this is not something only possible with entanglement. Okay. So what do I trying to do? Okay. So we have two systems, and we want to send. So Alice want to send the information to Bob. So some classical string. And okay. So now we are in quantum world. Sometimes you want to send information as classical string. Sometimes you want to send maybe a quantum state. But for the super dense coding, we'll focus on this one. Okay. We'll focus on we want to send a classical string. Okay. So think about how efficiently Alice can send classical string to Bob. Okay. And okay, we are doing both. Okay. Okay. Yeah. Anyway, what super dense coding is doing is that we say we can send two classical bits. Okay. So it's classical string because Alice and Bob classical want to send classical string. So we can send two classical bits by saying one qubit, and but also using a pair of shared entangled state. Okay. And what the shared entangled state is this. Okay. So it's this. Now we call it psi. Now later we'll have a better name for it. So we use the shared entangled state. That's a 2 qubit state, and it is 0, 0 plus 1, 1 square root 2. And we'll think about, okay, so this is shared entangled. So first this state is entangled between its first register and second register. And it's shared means that we are thinking Alice is holding 1 qubit of it, and Bob is holding another qubit. Okay. And yeah, so we have a picture here. So we are thinking we have this state, and Alice is going to hold one part of it, and Bob is going to hold one part of it. So how they get this shared entangled state is, so we are thinking communication. So Alice and Bob are kind of physically very far away, and then they want to communicate with each other. So maybe Alice create this state on her side and sending 1 qubit of it to Bob. Then now they hold this shared entangled state. So this is so we write it out. It has so this is 0, 0 is first register 0 is on Alice's side, and second register 0 on Bob's side. Oh, I'm writing this wrong. Okay. Okay. So this B should be outside. Okay. And and yeah, and this 1, 1 is also the first register 1 is on Alice's side, and the second register 1 is on the Bob's side. Okay. So we have a shared entangled state, and we say we have a super dense coding, saying that sending quantum information is things more efficient than sending classical information because you only send 1 qubit, then you can also convey 2 classical bits. Okay. And let's see how it works. So as we said at the beginning, they need to share the entangled state. So this is something I do beforehand. Okay, so let's start with the shared entangled state, and then set another qubit to to convey the 2 classical bits. And okay, So, okay, so let's say something that you might confuse you. So it seems like they are sending 2 qubit total here because they need to send 1 qubit to create a shared entangled state and send another qubit to send the actual message. But that's okay because this shared entangled state can be sent before they know the message. So we are thinking Alice will get some message, 2 classical bit messages sometime. And so maybe 00, 01, 10, and 11. And she want to convey this to Bob. So Alice is going to get one of these, and Bob should also get one of these, the same. After the protocol, Bob will know which one of those 4 Alice want to tell him. And so they can pre-share this entangled state, then Alice will get a message, then Alice can send 1 qubit. So that's why we say the shared entanglement state has no information because they can do this they can create this shared entangled state before they get the message they want to send. Okay. And okay, let's see the actual protocol. And so Alice wants to send 2 bits to Bob. And for the 2-bit message, there are 4 possible messages. So 00, 01, 10, 11. And the protocol goes as follows. So first step, Alice do something on her side, depend on which one of the 4 messages she want to send. So if it's 00, then she do nothing. And so the total quantity between Alice Bob is still this 00 plus 11. Okay. And on 10, then she applies Z on her part. And then we need to do some calculation. Okay. And the calculation step are here. Okay. So what is Z on Alice's part? So we think about on the 2 system is Z tensor identity. Because the Z only on the Alice part, nothing on the Bob part. And now I think about Z tensor identity on 00 plus 11. And there are multiple ways to do this. And by how we teach you about the definition of tensor product, you might think you can write everything in a 4-dimensional space. So you have 2 qubits and everything in 4-dimensional space. So you have 4-dimensional vector, 4-dimensional vector, 4-dimensional vector times a 4x4 matrix. And that's doable, but that's very hard. Okay. And the easier way to use the linearity here. So, okay, and here we are omitting this 1 over square root 2 to make a calculation a little easier to write. So think about Z tensor identity, apply on 0 plus 1, 1. But remember everything is linear here, so you can multiply this out. Okay. So it's a Z tensor identity on 0, 0 plus Z tensor identity on 1, 1. And now you have this Z tensor identity on 0, 0 and Z tensor identity on 1, 1. You see that everything is like a product structure here, right? The Z tensor identity and the 0, 0 is the actual 0 tensor 0. So you can just do the slot by slot rule. Okay? So this is just a Z apply on 0 and Z apply on 1. And similarly, this Z tensor identity on 1, 1 is just Z apply on 1 and identity apply on 1. And so Z plus apply on 0, so we have the Z Z matrix here. So Z apply on 0 will be just 1, and Z apply on 1 will give you a -1 sign. So the Z on 0 is still 0 and 0. And Z on 1, 1, so Z on 1 give you a minus sign 1, and still 1, and identity on 1 just give you 1. And then you add those two things back together, so you see it's 0, 0, minus 1, 1. Okay? So that's how you do the calculation. So Z tensor identity on 0, 0 plus 1, 1 gives you 0, 0, minus 1, 1. And similarly, you apply X, which is X tensor identity. So X on Alice's part is thinking about the 2 qubit system is X tensor identity. And so you think about X tensor identity on 0, 0 and 1, 1. And X is this. X will flip 0 to 1 and 1 to 0. So this 0, 0 become 1, 0 because this first 0 got flipped by x into 1. And the second one got flipped by x equal to 0. So this become 1, 0 plus 0, 1. And finally, if Alice's message is, okay, so Alice's message is 1, 0, then she apply x on her part. And finally, if her message is 1, 1, then she apply z, then apply x. Okay. And the ordering is a little important, but anyway. She apply z, then apply x. So apply z, then become this thing, then apply x. And yeah, apply x, then 0 become 1, and then 1 become 0. So become this 1, 0 minus 0, 1 state. Okay. So yeah, depend on what message Alice want to send, she will do these 4 different operations. And the shared entangled state between Alice and Bob will become those 4 different states. And those 4 states are actually pretty important. So they have names and they have names. For now, we call them, well, the easiest possible way to call them. So we call them beta 0, 0, and because it's for 0, 0, and then beta 0, 1 for the 0, 1, and beta 1, 0, and beta 1, 1. Okay. And for the, okay, let's go back to the protocol. So first step of the protocol is Alice read her message and do one of the 4 things on her part. And the second part of the protocol is Alice send her qubit to Bob. Okay, so Bob now has this whole entangled state. So both of the qubit is on Bob's side. So Alice do something on this particle, then just send it there. So Bob now has those 4 possible states. Okay. And what does Bob do is he will just do a measurement to distinguish those 4 states. Okay. And you can check in your homework. You will check in your homework to see that those 4 states actually form an orthonormal basis in your 2-dimensional space. And because they are orthonormal basis, then Bob can do a projective measurement to distinguish those 4 perfectly, because they are orthonormal to each other. So yeah, so Bob will do, say, the projective measurement should be like the projection onto beta 0, 0, and projection onto beta 1, 0, dot, 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 dot. And there's a 4-dimensional space, and you have 4 orthonormal vector here, so it spans the whole space. Okay. So Bob can perfectly distinguish those 4, and that already complete our protocol, because Bob knows which 4 of them, but we know those 4 corresponding to 4 different messages. So if Bob do the measurement and see the state. So for example, the state he got is beta 1, 0, then he know that the state Alice sent, sorry, the classical message Alice had is 1, 0. Okay. And any questions so far? Should not? Yeah. Let's talk a little about those beta states. Okay. And as we say, they are pretty important. And they have a lot of names. So those psi, we actually call it beta 0, 0. I think this is the one that we'll use most in our class because it's easier to remember and write. And they are called EPR pair. EPR stands for 3 physicists, and E is Einstein. But okay, it's a little confusing because EPR pair. I think EPR pair is actually beta 1, 1. But anyway, those 4 are really similar, so beta 0, 0, sometimes we still call it the EPR pair. And it's a maximum entangled state because yeah, it's also confusing because so all 4 of them are maximum entangled state because that's how there is some measure that you can calculate how entangled quantum state is, and you see that those 4 states are maximally on that. We'll talk about that a little bit on next chapter or next PDF. And anyway, so those 4 are kind of local EPR pair in the maximum entangled state, and they have different names. So if you see on Wikipedia, usually they will also write beta 00 to beta 11 as those 4 symbols. So this big phi plus, big phi minus, and big psi plus, and the big psi minus. So this symbol is the capital form of this phi Greek letter, and this is the capital form of this psi letter. But it's a little hard to remember which one it is. Yeah, and they're also called Biot states or Biot bases. So they are together are called is a basis, and it's called Biot basis, and which one of them is a Biot state. So so you see all those names, then they all kind of refer to those states. So EPR pair, maximum entangled state, Biot states, and they kind of all mean those 4 things. Although maximally entangled state can have other meanings, etc. So here's just some notation that might be useful when you read papers. And let's go back to the property we talked about, this pre-shear entanglement. So first thing, so now we see this a little more careful. So it doesn't contain information. So once again, you can pre-share the entanglement before. So this sharing entanglement doesn't depend on the message Alice got at all. So you can share this before you got the message at all. So it doesn't contain any information about the two classical bit you want to send. You can create it before Alice know what message you want to send. And so that's a little similar to sharedness, but you see that this is more powerful. So sharedness is like so share where should I draw? So for those of you who don't know sharedness, it's like Alice and Bob will flip a public coin. So beforehand, and so say Alice flip a coin. So she will get a 0, 1 with 50% probability, 50% probability. And then she send the result to Bob. So Alice and Bob now has some 0, 0 or 1, 1 with 50% probability and 50% probability. And so that is sharedness, and it's useful in some of the classical communication protocol. And but we didn't prove here, but you can pretty easy to convince yourself that even if Alice and Bob have sharedness, they cannot send 2-bit with. So even if they share a lot of sharedness, they cannot do the super dense coding where they send 2-bit by sending just 1 bit. Okay. So so shared entanglement is more useful than sharedness because you can do super dense coding. And but it's still a bit funny. So even though you can pre-share it, you still need to send 1 quantum qubit, 1 qubit to create this EPR pair. So I think it is 1 bit of quantum communication. So that's when Alice need to. So you can create this by Alice prepare the entangled state on her side, and then she send 1 qubit to Bob's side. So that's sending 1 qubit. And we can think of it as a resource, as in this is something that you want to create and consume when you do your protocol. So here we see that we create our shared entangled state before our protocol starts. Then during our protocol, we will consume the shared entangled state. because after the protocol, the sharing entanglement state got changed and sent to Bob. Then Alice and Bob don't have this sharing entanglement state anymore. Okay. Any question? Tricky. We have 4 minutes. I don't think we can finish teleportation, but we can. I guess we can say a little bit about it. Okay, let's flash about teleportation. Good. So, yeah, it's funny. So this is in book chapter 2.3, but teleportation is really similar, but actually in book chapter 1.3.7. And anyway, teleportation is kind of the opposite side of superdense coding. So this is where you want to send. So Alice and Bob still share entanglement, and but now they want to send a quantum message. So basically, they want to send 1 qubit from Alice to Bob. But now they only have classical channel. So they want to send a quantum message by sending classical message. Okay. So another thing, this is kind of impossible because, as we say, so Alice wants to send whatever state to Bob. Alice has this state, and Alice don't even know that state herself. So you have a state A0 plus B1. And as you see, if you want to classically describe this state, you have this A and B coefficient, and it's like two complex number, and there are using a lot of classical bits to describe this to have good precision. And so how can they at least send this to Bob with just 2 bits of classical information? Okay. This is pretty impossible. Like Alice cannot even learn this efficiently herself because Alice, because as we said last time, it's kind of hard to learn a non-quantum state. So Alice do a measurement, and so say Alice do a measurement on computational basis, then she will get a 0 or 1 with some probability, but then it's A, B information that got destroyed. Okay. So that's really weird. How does they do this is by having Alice never learn about this unknown state side, and they do some magic with their shared entanglement, and they will just teleport this side to Bob's side. So at the end of the protocol, Alice will learn nothing about this side, and Bob will have an unknown state side there that's still unknown to everyone, but they know that's the same state side here. Okay. And the protocol kind of I have 1 minute, so I have a very high level description of protocol. So Alice and Bob will once again start with sharing this beta 00, and Alice also holds this unknown state side that she wants to teleport. And basically what they do is Alice will measure those two things in Bell basis, and she will send a measurement result to Bob, and Bob then is able to recover psi on his part. Okay. So on this part they do Bell basis measurement. Oh, sorry. And we'll see the detail of the math later. And but interesting thing is that we have seen some information theory here. So as you know, it's very hard to learn this unknown state side, and it's actually important that while Alice do this protocol, she learn nothing about the side, so we don't break the quantum information theory about how many copies do you need to learn unknown quantum state. And so we will see this next Tuesday. Okay. And I think it's time to stop the class. So see you next Tuesday, and happy 中秋节。